All right. So today we have Andrea Ferrari tell us about free field realizations of boundary VOAs from 4 A-twisted 3D N equals to 4 theories. Take it away.
Yeah. So thank you very much for the invitation. It's a pleasure to speak here and to present with some delay the findings that have been announced in this paper. I'm glad it's finally happening. My goal today, if my slides proceed, yes, is to tell you a little bit about free-field realizations of vertex operator algebra that appear at the boundary of 3D n equals to 4 theories. And in order to start, I will try to provide some contextualization and give some motivation for why we might be interested in this. So let me try to recall a few facts about vertex operator algebras that appear in 4D that could be relevant later. So recall that there is a 4D n equals to 2 SCFT VOA correspondence where we can assign to a 4D n equals to 2 SCFT some vertex operator algebra that lives on a plane. And this VOA emerges as the cohomology of some odd nilpotent operator Q that makes this operator stick to the plane and behave in a holomorphic way. So the VOA is a rich algebraic invariant of the parent 4D n equals to 2 SCFT. And perhaps it's even a complete invariant if you are interested in local data, local correlation functions. Now, since this is a Quiver, not a VOA meeting, I've tried not to assume too much knowledge about VOAs. However, I'd like to remind you of a couple of facts. First of all, we have a notion of operator product expansion, meaning I have two operators on my vertex operator algebra plane. I can try to collide them, and some other operators will appear at meromorphic singularities like this. Moreover, another important fact that I'd like to remind you of, or to tell you if you have never heard of it, is that I can associate to a vertex operator algebra some variety, which is called the associated variety, unsurprisingly. And the way in which it is constructed is that I take a quotient of my big VOA that you can think in terms of a big algebraic object. And this quotient, which is much simpler, behaves a little bit like functions from some space, particular functions from this variety. So the VOAs coming from 4D n equals to 2 SCFTs are expected to have some very remarkable features. In particular, the associated variety of this vertex operator algebra is expected to be the Higgs branch of the 4D n equals to 2 theory. For people who know a little bit about vertex operator algebras, this implies in particular that V is quasi-Lie. It satisfies some finiteness properties that make it behave in a fairly nice way. V is moreover expected to have a free field realization, to have free field realizations modeled on the low energy theory on the Higgs branch. Now I just told you that we can extract an associated variety from the vertex operator algebra. And one natural question is whether I can go back, whether the associated variety knows or can characterize the VOA completely. Maybe I'm just quantizing in a chiral way some functions on this associated variety. Maybe I need some little more information to derive it. And these properties are related to what in the vertex operator algebra literature called chiral freeness. But in the context of this talk, I'd like to emphasize that related to this point, there is an expectation that we may at least get some very nice presentation of the vertex operator algebra, given in terms of elementary building blocks modeled on the geometry of the associated variety. So these building blocks will be free bosons, free fermions. And if I get such a presentation, I can maybe go along and try to study characters of modules and so on and so forth, maybe in a nicer way. However, the free field construction in 4D is often ad hoc. So even The geometrically inspired one are usually given by I take some ingredients based on the geometry and try to play with them in order to obtain a nice presentation. However, the context I'm more interested in today will be 3D n equals to 4 theories. So let us try to remind ourselves a little bit better what happens in there. So 3D n equals to 4 theories enjoy two topological twists called the A and B twists. And we know since a few years ago that these allow for some particular boundary conditions that are chiral and can support VOAs. So this TQFT VOA correspondence can be construed as a generalization of the Chern-Simons WZW correspondence that was first pointed out by Witten, but it's much richer and wider because these cohomological TQFTs that we're looking at behave in a bit more of a wide way. In any case, we expect bulk line operators in 3D to act as modules for this VOA, meaning that if I pierce the plane, I can act with some local operators in the VOA and change what I have here. So they act a little bit like modules. Moreover, or as a consequence of this, there is this expectation that if I have a vertex operator algebra at the boundary, I'm able to reconstruct the topological local operators in the bulk by looking at the self-extensions of the vacuum module. So here I have an identity line, here I have an identity line, and what sticks in between them is going to be a local operator in the bulk, which is going to be in the A or B twist, either a Coulomb or Higgs branch operator. So my main motivation was to transfer some of the 4D n equals to 2 ideas to the 3D n equals to 4 setting and improve a little bit upon them. Now we can consider a naive reduction of the 4D setting, meaning I have a VOA that I put on this plane here, and my R2 direction I try to put on a cigar geometry, and then intuitively I try to squash this cigar to get a line. And what I get is precisely a 3D setting where I have a VOA living at the boundary of this half line. So we would expect, and there are some of our friends that I believe are working on this to make this precise, to land on the topological A twist of a 3D n equals to 4 theory with some deformed 0-4 boundary condition, which are these boundary conditions that support the vertex operator algebra. The Higgs branch of the 4D theory and of the 3D theory are the same. And so one reasonable expectation is that in the A twist of 3D n equals to 4 theories, with certain boundary conditions, the associated variety, the support via vertex operator algebra, the associated variety is again going to be isomorphic to the Higgs branch. And by mirror symmetry, in the B twist, we would expect the associated variety to be isomorphic to the Coulomb branch. Now, this interplay between the vertex operator algebras that live at the boundary of 3D theories and vacuum geometry is incredibly rich. And I have several projects related to this, so stay tuned. But I'd really like to emphasize these two branches that control two different aspects of the VOA. One is is expected to be the associated variety, and the other branch is expected to govern more the category of modules. So my goal for today is very limited and tell you some shadows of this phenomena. In particular, I will consider some simple 3D n equals to 4 Abelian gauge theories in the A twist, like super QED2 and some generalization. I want to show you how I can prove that the boundary VOAs have several free field realizations. This is unlike in 4D. And I want to show you that these free field realizations can be understood or interpreted as coming from some localization procedures on the associated varieties. Moreover, I want to show you that I can prove that the emergence of outer automorphism symmetries of this vertex operator algebra are related to Coulomb isometries. So this is a very simple way in which this VOA knows about these two things. So let me make a couple of remarks. First of all, unlike in 4D, we can explicitly derive a free field realization from first principles, like write down what the VOA should be and then prove that it has a free field realization. So we've particularly done this for abelian theories, working on generalizations. Moreover, this is kind of fun because the Higgs branch geometry or the Coulomb branch geometry in the A or B twist can tell us how to free field realize or are related to the free field realizations. And from this, we are able to derive facts about bulk local operators that are related to the other branch. Are there any questions so far? Okay, if not, let me go ahead. So I'm now gonna try to introduce a few elements that are gonna be our building blocks. And these are free fields and some bosonisation techniques. So my building blocks will be in particular, some free bosons and so-called half-lattice VOAs. So free bosons are just a collection of chiral bosons with some 2-point functions. And I can extend them based on a lattice along some direction. In this case, sigma minus rho. And then I can introduce currents for these bosons that have this singular behavior here. And moreover, I can extend based on this lattice and add these vertex operators in directions that live on the lattice, which have this OPE structure. Another collection of things that I'm going to use are so-called beta-gamma systems. And there are simply two bosons whose OPEs simply satisfy this property here. Moreover, I'll also have free fermions and BC ghost systems, but I really like you to focus on these half lattices and beta-gamma and beta-gamma systems to start with. So the structure that I've just shown should remind you of something well known, like this half lattice vertex algebra looks a little bit like functions on T star of C star, where I've replaced these Poisson brackets here with these OPEs. The beta gamma system, on the other hand, looks a little bit like functions on T star of C. In fact, I can take coordinates that are like beta and gamma, and their OPEs that I had written here looks a little bit like the Poisson bracket between x standard coordinates x and y on T star of C. In fact, there is.
Can I ask
sorry.
a very basic question? Why half lattice?
It's because we are not taking. We are taking only one direction, the possible lattice of linear combinations of these guys.
Thanks.
Sorry. So there is a very precise way, actually, in which we can make this analogy work. And so you can think of the fields that span this or generate this VOA as chiral differential operators on C or C star. So these are so-called chiral quantizations of functions on T star of C star and T star of C. So our free field mantra, to call it that way, is that to obtain a free field realization, we should look for openly embedded subsets of the form T star of C and T star of C star inside our associated variety, and try to use those to express the vertex operator algebra. So these constructions that I've just explained can be related via techniques that are called bosonisation. So in terms of the analogies with finite dimensional geometry that I was trying to emphasize, these are really like localization of functions from T star of C to T star of C star. If I have, in particular, a beta gamma system, I can embed it in some half lattice in two different ways. I can try to use a map like this, where I have this bare vertex operator and this other one decorated by the row. Or I can use a map like this, where it's now beta that gets a decoration. So intuitively, from the point of view of finite dimensional geometry, here is like these operations are the analog of inverting either x or y in the coordinates on T star of C that I tried to show before. Moreover, the images of these two embeddings can be thought of as the kernel of some screening operators. So I have a map from my beta gamma system into a half lattice, and I can check whether I can build a complex. I can build a complex with by adding a map here, and in fact I can. And what this map does is to look for the chiral equivalents of the inverses of beta and gamma. So basically, I can build this complex and check whether what I have here originates from this embedding or not. Now, free fermions can also be bosonized in two ways. In particular, I can add a further chiral boson if I want to bosonize two complex fermions. I insert another lattice, and I can embed my free fermions in this way. And I still have two ways to do this, but this is a little bit silly. There isn't that much of a difference. It's more of a convention. In any case, I can reproduce this boson in the lattice or the current associated to this boson simply by taking normal ordered product of the two fermions. And this is a famous isomorphism. I don't need screening charges. Like this Bose-Fermi correspondence is really an isomorphism. May I ask how I'm doing with time?
You have 40 minutes.
Okay, great.
Or more, actually.
Yeah. Okay, great. I'm going fast. All right. So I can tell you a little bit about, finally, boundary VOAs for this A-twisted, at least super QED2. So I don't have to introduce super QED2 to this crowd, but this is a 3D n equals to 4 gauge theory with gauge group U1 and two hypermultiplets in the representation +1. So these have two scalar components of charge +1. And the Higgs branch is a simple example of a hypertoric variety, namely the A1 singularity. So algebraically, what I can do, I can look at the ring of functions of this variety, and they are the ring of gauge invariant functions of my scalar field on the inverse of the zero locus of the complex moment map. So if I write this out in full, I can write this in terms of three functions that I call E, F, and H that satisfy some equation, which is precisely the equation defining the functions on the A1 singularity. Now, I want to consider a boundary VOA supported on some boundary conditions for this theory. And for the A-twist, what people choose to make something that supports a VOA are Neumann-Neumann boundary conditions, meaning Neumann for the vector multiplet and Neumann for the hypermultiplet. So if I let the boundary be at t equals to 0, and let indices run this way, at the boundary, my bulk fields, these bottom components, x and y, restrict to some beta gamma systems, which are precisely the beta gamma systems I introduced before. Moreover, there is some gauge anomaly that arises from putting Neumann that I have to cancel by introducing some boundary fermions of gauge charge +1. Gauging is then performed by introducing some Visigoth systems and taking cohomology with respect to the zero mode of this U1 current that I can build. Basically, I can pair my beta gamma systems and my free fermions, get some current. If I add this Visigoth, it's then squares to 0, so that I can build a differential that squares to 0. And I'm supposed to take cohomology with respect to that. And this is obviously very similar from the symplectic reduction that I showed you before. In fact, it can be thought of as a chiral analog of the symplectic reduction. In this case, I have these fermions that go along for the ride, which are related to this anomaly cancellation. But yeah, it can, as I said, these are there to cancel the anomaly. It can be thought of as going along for the ride. More formally, these sort of things can be expressed in terms of the relative semi-infinite cohomology of Voronov. This is an important technical point that, however, I'll gloss over in this talk. I will only mention a couple of results. Another thing that I wanted to mention is that these Neumann boundary conditions break the topological symmetry at the boundary. This is because essentially the normal component of the curvature of the gauge connection at the boundary is free to fluctuate, and so you can have inflow of charges from the bulk. But there were some suggestions that it can be restored by the presence of these fermions. And in the rest of the talk, I'm gonna try to tell you that this actually happens, that these boundary vertex algebras can actually see the topological or Coulomb isometries in a very interesting way. So in this simple example, what we obtain is what is called, by performing this BRST reduction, is what we call PSL2/2 affine Desmodi algebra at level 1, or a simple quotient thereof. And this notation is all that means. If you don't know much about this sort of stuff, naively, you can think about the following. We have some generators, which are these beta gamma systems that I can pair because they are gauge invariant. I have my fermions that I have added that will build my other two. And then I can have odd generator, and sorry, I have these odd generators here. So this will form a 4-block matrix with 2 even entries, this one and this one, and 2 odd entries, this one and this one. However, not all of these combinations are gonna survive my BRST reduction. In particular, I'm gonna have a direction in, or let's call it a direction, but a combination that is not closed. If I try to act on it with my BRST differential, does not vanish. And I also have an exact direction, which is the one that is basically contained in the BRST differential. And the effect of these two things is to remove the traces in DSL2s as well as the overall trace. So I go from U2/2, which is built out of these guys, to PSL2/2. Now, one question I want to ask is whether we can systematically solve the BRST reduction and free-field realize this very nice vertex operator algebra. And what I'd like to say is that, yes, we can do that. The strategy is to bosonize, use lattice VOAs and half lattices and so on and so forth, and then find a nice basis in these lattices that solves BRST for us. So this is the strategy that I'm going to try to highlight now and I will present you two different free-field realizations that will hopefully show two different features. Are there any questions so far? All right, then let me proceed. So let me try to tell you how to obtain one first free-field realization. So if you recall, for this VOA, we have collections of two beta gamma systems, which were the fields coming from the bottom component of the bulk hypermultiplex. And we also have pairs of free fermions. So what I can try to do is to bosonize everything to obtain some expressions that depend on simply free bosons. So for my first free-field realization, what I'm going to do is, for later convenience, is I'm going to bosonize things in an asymmetric way. For one pair of the beta gamma systems, I will sprinkle my d rows to the gamma. For the other pair, I will sprinkle my d rows to the beta. And accordingly, I can bosonize free fermions in an asymmetric way. But again, these are isomorphisms just for convenience in science. When I do this, I can then look at what my differentials in the BRST complex become. And so I'm going to have, if you think about the lattice spanned by these chiral bosons, I'm going to have what I call an exact direction. Meaning that if I take some linear combination of these bosons, the BRST current that I wrote down before is simply going to be the defined U1 current along this direction. So I take D of this, and it's basically what's contained in the BRST differential. Moreover, I can take a non-closed direction, meaning a direction whose OPEs with this guy here is not going to be 0. And this is, in fact, the derivative of this guy is going to give me the non-closed current that I wrote up here. And then if I do that, I can try to complete my basis to express all of the possible other linear combinations of these chiral bosons in a way that it does not interact with the BRST differential and my non-closed directions. And I can do that, and I'm going to get two bosons, which I'm going to call phi and delta. And I'm going to have two pairs of complex fermions that are the fermions that I had before. Recall they were exponentials of this omega-1, but now decorated by some bosons. And an important point is that these fermions will carry an outer automorphism index, meaning that I can act on them and rotate two of them amongst each other so that the OPs don't change. So let me make a few remarks. First of all, the BRST problem in the new variables simply concentrates in the eta1 and eta2 direction and can be solved by using some extremely powerful vanishing theorems of Voronov. So if you express your cohomology BRST cohomology in terms of this semi-infinite cohomology, you can actually demonstrate that the BRST problem along those two directions trivializes. In practice, what we can do is that we express closed fields in an eta2 independent way, meaning that they are not supported along any non-closed direction. And whenever I find an exact one, I can essentially cross it out. Now, there are a lot of subtleties in this procedure. For example, notice that I had to refine my lattice in order to define my fermions in an appropriate way. Here I have some halves that I was before not allowed to take. And so one has to and must check that the BRST cohomology of the original problem fits inside the obtained cohomology in the new variables, and that nothing goes wrong. And this is indeed the case. And although all of these are a bit technical, the final result is fairly intuitive to understand, and I can still express it in terms of the kernel of some screening charges. So, okay, this is the whole procedure. Basically, find a change of spaces where I can solve the BRST problem completely, and then try to go on and find a suitable set of generators. So what happens if I apply this procedure to my beta gamma fields that I had in my original VOA? If I do that, bosonize, as I told you, in this way here, do my change of variables, and cross out the exact terms and so on and so forth, what I obtain is this very nice presentation where I have three fields, E, H, and F. E is basically the exponential of delta plus phi, H is d phi, and F has this nice form here where now this tip psi is a stress tensor built out of the fermionic trace. Now, for people a little familiar with vertex operator algebras, even in this extremely simple and elementary example, this is an interesting result, because what we are doing is the following. When tip psi is 0, we can reproduce a famous construction given by Adamovich that realizes affine algebras based on the algebra SL2 at level k for a restricted k that lies in a restricted set of fine-tuned set of levels. But now here, this stress tensor that is built out of our fermions comes to the rescue to adjust the level and get the right one for our original collection of beta gamma systems. Now, this fact is actually key in this particular free-field realization. It's a fact that generalizes to all the Abelian examples. And this is the mechanism that allows us to basically to solve completely the BRST reduction, in meaning that we don't have to impose any further quotient on this algebra. These are really the generators for PSL2/2 at level 1. Notice that this is not always the case. For example, other free-field realizations of precisely these vertex algebras have been introduced in the past to study, for example, ADS3 CFT2 holography. But depending on your needs, you might or might not have this very remarkable feature. But what I'd like to emphasize a bit more today is, well, we can ask ourselves what is going on at the level of the Higgs branch geometry. Recall that I had introduced above some functions on the Higgs branch, which I'm calling E, F, and H. And if I take all of these analogies that I was dreaming about the talk, I can see that I have this E to the delta plus phi, which looks like an invertible guy. So in fact, when I write this, not this. When I write this, all I'm doing, it seems, is to invert E and express F in terms of E and H, and something else that comes from the fermions. But if I take a naive analogy, what I'm doing here is I am trying to just invert this function here and solve for the defining equation of the I1 singularity in a way that I can express F in terms of E and H. In fact, you can understand this as just adjoining an E minus 1 to the coordinate ring of A1 to get functions of T star of C star. And this is compatible with the free field mantra I was telling you about before. The difference here is that we derived it from first principles. We constructed the free field realization explicitly, and now we are reinterpreting it in terms of localization on the associated variety. So now let us take a look at the odd generators. I will not, I'm gonna bore you with the full presentation of the whole thing, but a very interesting feature is that these odd generators manifestly carry a symmetry, this SU2 outer automorphism symmetry that was owned, so to speak, by the fermions. In particular, I can write, somewhat miraculously, it seems, these odd generators in a SU2 covariant way. This only happens after some manipulations, but then you might ask yourself, well, why? Was I bound to have this SU2 automorphism carry over? And one way to think about it, which is an explanation for this phenomenon, is that if you think about how the screening charges look like, then you can recognize that they transform into a representation of this SU2 outer. So I had this outer automorphic symmetry at the level of free fields in the big free field algebra containing all of the fields. But now my screening charges transform nicely under this SU2O. And so this property basically is transferred to the vertex operator algebra itself. So this is all very nice, but there is an alternative. In particular, remember that I had picked some particular choice of bosonisation. Therefore, I want to discuss what happens if I take another route and instead try to free field realize in a different way. Any questions so far? If not, I'm gonna go on. So let me tell you about this second free field realization. So I still play the same game as before. I introduce some free bosons, which have some particular features. And then I consider some embedding of these free bosons, of my beta gamma systems and the free fermions into a big free field algebra. I bosonize everything. This time I do so in a correlated way, meaning that now my D rho 1 is inserted here, my D rho 2 is inserted here, and there are beta 1 and beta 2 that are not carrying any of these. And again, I can do the same with the free fermions. This is not very important, but it would help us to keep track of some signs. And everything goes through as sorry, the type was before, but now following the finite dimensional analogy, E is no longer invertible. Why is this the case? I'm not writing down the full expression here, but E, roughly speaking, is beta 1 gamma 2, and now I have this D rho 2 here that spoils the feature I had before that it was an exponential. And H is certainly not invertible, and F also is certainly not invertible. So in fact, we're not localizing with respect to any function on A1. However, I would like to claim that provided we resolve this A1 singularity, I can still find an open embedding T star of C star into T star of P1, which is a resolution of this A1. So it is perhaps time for some hyperplane arrangement that will maybe give you an idea about how these statements actually generalize to all the Abelian cases. So let us try to resolve the Higgs branch by introducing some Fi parameter, zeta. And then when people look in hypertoric geometry, and there are certainly people more experts than me in the audience, but is to look at a very particular subset of these hypertoric varieties, which is called the extended core. So what I'm doing is I'm putting all of the, so there are some gauge invariant combinations that are the flavor moment maps in physics terms. I set all of those to 0. And then I consider my variety as a vibration over the value of the real flavor moment map. In this case, I'm adopting conventions so that this flavor moment map looks like x2 squared minus y2 squared. On the extended core, I always need to choose for each pair whether to set either x or y to 0. In this case, if I set y1 and x2 to 0, you can see that my flavor moment map needs to be negative. If I set y2 and y1 to 0, then if you take into account the real moment map constraint for the gauge symmetry, it actually tells you that these values here is between 0 and zeta. And the same holds here. You can check that possible choices are, say, set x1 to 0 and y1 to 0. Now, then what happens is that on this line, fibered on this line, on this locus here, I will have an S1 that shrinks when it hits some hyperplanes that are precisely these values here, 0 and zeta. And so what is happening now? So if you think about the finite dimensional analogy I was trying to promote and advertise, if I declare that that x1 is non-zero and y2 is non-zero. Oh, sorry, I should say before of this that the hypertoric variety is actually the cotangent bundle to the C that I see here. So if I remove, if I declare that x1 is not 0 and then y2 is not 0, as we have done in the first case, then I'm going to kill all of the regions that I had here, but this one. And this is actually, you can actually be seen as T star of C star, where C star is this basically S1 vibration over R. And in this picture here, sorry, I'm also removing the origin. So I found some T star of T star indeed by removing all of these subsets. And moreover, when I remove my resolution, the subset in the first case survived. So this is a very bad way of saying that I can find an open embedding of T star even in the unresolved singularity. If I do things as I was doing in my second way, I still find some T star of C star. Indeed, it's the cotangent bundle to this sphere here without these 2 points that I'm completely removing because I'm removing these 2 regions. However, the T star of C star that I found does not survive if I remove the resolution. And in fact, I was trying to tell you here that the finite dimensional analogy of my field realizations looks like it is such that I do find a T star of C star inside a resolution of the singularity and not the singularity itself. So if you write down some hyperplanes arrangement and think a little bit about, in terms of hypertoric geometries, what is happening. So it seems that we are kind of forced to resolve in order to make sense geometrically of our free field realization. But then let us look at what happens to the odd generators, because resolving is in some sense a very physical thing to be doing. And in fact, I should be lifting the Coulomb branch. Very remarkably, the automorphisms in the odd generators are no longer manifest. In fact, I can show that if before, after bosonizing in my preferred way, I found that the screening charges transform in some representation of the SO2 outer automorphism symmetry. Right now, this is not really the case. And so this nice outer automorphism symmetry that was carried out by the fermions is no longer passed on to my odd generators. Physically, this is consistent with the fact that indeed NFI parameters breaks the topological symmetry. And so my free field realization doesn't know anymore about its existence. Finally, I'd like to point out that there are other ways to resolve. And if you resolve in other ways, you might obtain other hidden T star of T star, which are compatible with other choices of inversion. For example, I could make a bad choice of inverting either x1, y1, x2, or y2, and kill everything over my fibration. However, if I do so, I can take my zeta and tune it so that it becomes negative and recover another nice T star of C star. So this is an instance of a phenomenon that generalizes to the theories we looked at, which is if you close your eyes and pick at random some bosonisation in order to solve your BRST reduction, then there will be some resolution parameter that actually allows you to land on an empty T star of C star that is openly embedded in the hypertoric variety. Now, I think it is worth emphasizing what I call a mirror picture.
So I have
because, yeah.
So the free field realization one you had, is it better? Like, is this a statement one can make?
Sorry, is
it better?
Yeah, it's better. The first one is better in a sense that it manifests all of the outer automorphism of the vertex operator algebra. So this acts linearly on the fields.
Mm-hmm.
This is no longer on the free fields. This is no longer true in the other one.
Okay.
It's obscured.
The thing that if you find some realization, then it may not be that good, but it always works if you pick a resolution.
Yeah, so the claim that we make more generally, I will get into that, but is that if you find some open subset in the associated variety that is embedded in the unresolved space, you don't have to turn on any physical parameter to resolve it, then this thing is going to manifest all of the symmetries that you have. And these are manifested by acting linearly on the free fields.
Okay, thank you.
And so there is this mirror picture that I want to emphasize because I believe it's quite important for generalization from Abelian theories and so on and so forth. So let me tell you what I mean by that. So we can look at the A1 singularity as the Coulomb branch of the mirror theory, which in this case is the same. So let me say that my Higgs branch is the Coulomb branch of SQED2. And here I'm denoting it by saying that it's the Coulomb branch of U1 with 2 hypermultiplets. Now, if you know a little bit about Coulomb branches, on general grounds, we know that there is some ring homomorphism between the Coulomb branch of a theory with some matter and the Coulomb branch of a theory with less matter. In this case, in particular, I can remove all the matter and I can find a homomorphism between, by redefining the monopole operators, between the Coulomb branch of a theory with U1 and 2 hypers of charge 1, and the Coulomb branch of a theory with U1 and no matter at all. But in the Abelian case, surprise, surprise, this Coulomb branch of pure gauge theory is simply T star of C star. So what I've done in the first case, or what I did is can better interpreted as saying that if I look at this guy in terms of a Coulomb branch, I've localized with respect to some monopole operator, so that this famous homomorphism actually becomes an isomorphism. So I take the Coulomb branch of SQED2, I invert a monopole operator, and I go down to the Coulomb branch of pure gauge theory. And I'd like to stress this because it's related to some very fancy and interesting technology that has been developed in the context of restriction functors between certain Coulomb branch algebras. So if you have some algebras associated to Coulomb branches, for example, or let's say some algebraic object like the ring of functions, there are some techniques that allow you to restrict things to, or to map things from things with more matter to things with less matter. And there were a couple, at least one important paper about this fact 1 year ago, I guess. So let me briefly mention about generalization. It's going to be just a couple of slides, or maybe only one. But more generally, we can prove the following. So for a good enough Abelian gauge theory with rank K and n hypermultiplets, certainly this holds for good theories, but more generally, the conditions that I am imposing is that the associated variety has no residual gauge symmetries at any point. So it's related to some unimodularity conditions in the lattice of charges that I'm picking. But in any case, for a good enough theory, there are 2n choices of bosonisation, like 1 for each hypermultiplet. And for each of these choices, I can rigorously produce a free field realization. We can, moreover, identify such a free field realization with an openly embedded subset T star of C star to the n minus k, which is the dimension of this X branch, for some resolution parameter zeta. Meaning I start by picking at random the T star of C star or inverting random things upstairs before gauging. If I naively do the symplectic reduction of a torus by a torus, roughly a torus, and I did get a torus, but I claim that furthermore, I can openly embed it into some resolution. If this open subset survives when I take the limit zeta goes to 0, then I can prove that the automorphisms symmetries that are manifested by these free field realizations reflect the enhancements of the Coulomb symmetry. From a mirror perspective, we have then an isomorphism of these open subsets when this condition holds, that I can go to the unresolved case. We have an isomorphism between these open subsets with the Coulomb branch of some pure rank K gauge theory hidden in this Coulomb branch. So in the paper, we discuss much more. One interesting thing is like the bosonisation. What does that mean? I told you that in my free field mantra, I didn't necessarily want to land on functions on T star of C star. In fact, beta gamma systems are good enough for it, meaning that if I find functions on T star of C, I'm already happy. But the bosonisation techniques require me to go down to the torus, the quadrature bundle to the torus first. And then I have to ask myself the question whether I can debosonize some of the things that I found to go, for example, from T star of C star of n minus k to T star of C star to the n minus k minus 1 times 1 copy of T star of C. And if you think about it from the Coulomb branch perspective, it's quite interesting, because what I'm doing is that the Coulomb branch of super QED1 is T star of C. So I may try to invert monopole operators to land not on pure gauge theory, but on super QED1. And this doesn't happen in super QED2 case, but if you look at higher super QED, this actually happens, and you can reproduce by these observations some very remarkable free field realizations based on beta gamma systems and T star of C star that arise for minimal nilpotent orbits. So the geometry of these patches is very nicely related to these sort of considerations. In conclusion, I'd like to tell you a little bit about problems related to this, things that I'm interested in looking at, and tell you why I believe this thing is quite remarkable. So as I said, so I see this as just a first step towards the understanding of how the geometry of the Higgs and Coulomb branches affect boundary VOAs in this very remarkable TQFT VOA correspondence in 3D. And besides obvious generalizations and clarifications, like obvious generalizations, like can I generalize this to non-abelian cases in a reasonable way? Can I understand the actual physical realization of screening charges? Can I understand the emergence of associated varieties from the physics a little better from an intrinsic 3D viewpoint? And these are all problems I'm thinking about. But besides obvious generalizations and clarifications, if you want to study the interplay between these two things, like I have two hyperkähler varieties that are trying to, if not determine, constrain my vertex operator algebra, one easy thing to look at, or supposedly easy, is you can ask yourself, well, what happens when the Higgs and the Coulomb branch are both points? In that case, I can no longer build a free field realization out of the associated variety, it's just a point, but maybe some other things happen. And in fact, what I expect would happen is that we may get some vertex operator algebras enjoying some finite properties like rational conformal field theories. And so I'm working on a set of examples that will actually give some evidence that this is the case. And moreover, another thing that I believe is very interesting to look at is the interaction of these geometric pictures for these vertex operator algebras with what in physics we can call extended Higgs and Coulomb branch geometries, meaning that we try to decorate these varieties by keeping track of a little more of the low energy theory, of the low energy physics on this vacua. And these are long-standing projects that I've had in trying to understand a little bit some of these TQFTs that arise in 3D as vibrations of categories on the associated varieties. And so, but what I would like to say is that there are questions to be asked concerning the interaction between these topological TQFT subsectors and the vertex operator algebras. And geometry can be a nice interpreter for this sort of phenomenon. And moreover, this leads to obvious and interesting mathematical questions, like to actually prove that associated varieties are the Higgs branches and so on and so forth. Doing it case by case is very hard, but maybe the physics is telling us something about how to solve these very important problems in the theory of vertex operator algebras. Yeah, and this was more or less the end. This is all I wanted to tell you guys.
All right, let's thank Andrea. Are there questions?
Yeah, I have a few questions. So you described these free field realizations starting from some smooth open subset of the variety. Could you say something about how you go to the closure?
I mean, this
are you missing something if you don't?
No, the expectation is that I mean, for this sort of subsets that you get by inverting one function or so on and so forth, you shouldn't miss much.
So you don't expect, I mean, I could imagine that you might miss even a symplectic leaf or some symplectic leaves by doing that. You think
right.
that's not the case?
Well, you want to avoid that situation. You want something that is, if not dense, at least close to be dense into the original space.
So, but I don't understand. Is this an expectation theorem, or it just comes
no,
out?
It's an expectation. I don't know. I mean, these examples I worked on, all the subsets that we were finding were completely, I mean, were enough in order to reconstruct everything. And I don't have a theorem. Or something that I have to say is that, I mean, these considerations based on physics still need to be proven in the vertex operator algebra context. I mean, building free field realizations out of localizations on associated varieties is something that requires a lot of machinery and work to prove. And so what is remarkable about this Abelian case is that we can try to get these free field realizations in a very rigorous way, and then a posteriori check that we get these subsets that seem to be enough to reconstruct everything.
Okay, and thanks. So one final question is, well, sort of related to what I was asking earlier. But you might think or hope that there could be a free field realization for each symplectic leaf, in fact, because then what you have is smooth, so you should be able to describe it in terms of free fields, and that would be kind of more natural. Say if you're interested in also say the connection to maybe the low energy physics, the symplectic leaf seems more natural. But the examples that you showed were not of this sort. Have you tried looking at free field realization, say, for a given symplectic leaf?
No, I mean, this is what I could do by, so the goal of this project was to really try to derive these free field realizations from first principles, and then a posteriori identify what was going on. And so I haven't looked at other examples, no.
Okay, thanks.
Okay, good. Do we have more questions? Well, if not, then I'd say let's thank Andrea again.
Thanks.
Now stop the recording.